hear me back there? Okay. So this is really the homework, which is what would you do to design this thing? What kind of fuel would you use? How would you direct it to go from point A to point B, and so on. So what I want to do is talk about how you try to design motors of this kind that are self-propelled. Now, when Baker invited me to talk here, I thought she forgot about mine. I must be the only chemist here, and I'm not even a physical chemist. I'm a synthetic chemist. I do not understand equations. So I have very, very few equations. But also, to be fair to you guys, I also have very, very few chemistry equations. So what I'm hoping to do is to ask at least as many questions as you are asking, trying to understand what's going on behind these things that we are designing. And if you have good ideas, for every good idea, I'm happy to buy you your favorite beverage. So,
how do you measure that?
How do I measure what's your favorite? You should know it.
No. The good ideas.
Fine, I'll just buy you one. Just tell me what your idea is.
I like that.
So I'll just keep going and no particular set point. Okay, so that's what I want to talk about in the next three talks, which is how do you design active matter that might mimic some of the beautiful things that you have been seeing in biological systems. How would you power them? One of the interesting questions is how do you convert power in the form of chemical energy? You've heard about ATP being converted to ATP and PI, which is the source of power for most biological systems. What remains a mystery is how do you convert that into mechanical motion? A lot is known about ATP motor. Nobel Prizes have been given for that. But by and large, it's not a very well understood field, how you convert reactions, energy gain from reactions into mechanical motion. And then the other nice thing about biological systems is they talk to each other. And I would like our things, particles, bots. I like to use the word bots because it sounds edgy. How would you have them talk to each other and signal to each other and so on and so forth? So that's the general idea. So this is taken from one of the Department of Energy calls for a proposal. I guess they like to think big. How do you master energy and information at the nano and micro scale? So this is extreme synthetic biology. That is biology without biology. How do you create technologies that would rival those of living things? Requires designing intelligent systems, and of course, what constitutes intelligent systems depends on who's talking. But one thing is clear, that chemists are very, very good at driving things to equilibrium. When we mix chemicals and we try to make a new compound, all we're doing is mixing the chemicals and waiting for equilibrium to happen. But that's not where the fun is. The fun is when we start to drive things away from equilibrium. And as chemists, we really don't know how to do this very well. So we'll talk a little bit about this. Now let me try to define what in the system that I'm going to talk about, mean by intelligence. So it's two things. One is you need information, and you need something that will act on that information. So let's just call it an information process. And one without the other is, of course, no good. So how do I input information? Well, how does biology input information? Mostly through gradients. Chemical gradients, light gradients, thermal gradients. Those are the typical examples of information input in biology. And the information processor is the self-powered object. So, for example, if you're hungry and you smell a hamburger or nearby McDonald's, there's a chemical gradient there, right? And as you go closer and closer, it gets stronger. So that's your chemical gradient, and you are the self-powered object. And so you respond to the gradient by moving. So the information is the fact that you can smell that hamburger or those two golden arches up. And you're the self-powered object. So the result of the combination of these two would be some kind of collective emergent behavior. Depending on how hungry, it could be a stampede. And so then there's an assembly at the McDonald's. So it could be in space, it could be in time. So that's what we're trying to do is trying to put these things together to form different kinds of assemblies that will do different kinds of things. So, of course, both of these would require energy. To sustain the gradient, you have to have energy. If it's a gradient of light, then you have to have light source. If it's a gradient of chemical, you have to have a chemical source that's emitting. And also, to power the object, you need energy. So the three design principles that I want to talk about, first of all, how do you move things? In biology, it's always by catalysis. You do a chemical reaction, you drive the energy, and somehow you convert that into mechanical motion. So the question is, how many different ways can you convert chemical energy into mechanical motion? And although I keep talking about particles or balls or what have you, this also applies to fluids, and we'll talk about that. So the question then is, what are the different ways you can move an object? Second, if you have learned how to do that, the next question is, you want them to move in a certain direction, not in some arbitrary set of directions. You want them to move from point A to point B, do some work, etc., etc. So how do you control the directionality? And I've sort of already told you, we want to do it by supplying information in the form of a gradient, a chemical gradient or a light gradient. And finally, we really like them to talk to each other and do things collectively. And the question is, how can they communicate? And I'm talking about nano and micron-sized particles. So I'm not talking about large objects where you can put a sensor in and a battery pack and all of that good stuff. So that's what I'm going to be talking about in 2 or 3 lectures. And we'll see how far we get. And by the way, if you have any questions, just raise your hand and bother me, because more often than not, I'll just say I have no idea. We'll see. Since it's a physics school, I thought I should at least pay homage to Richard Feynman. So he said, what I cannot create, I do not understand. Of course, he was talking in the context of theory. I'm an experimentalist, so in my case, if I can't make it in the lab, then I really don't understand how things work. Most chemists come up with chemistry sets. Those are fun. You could set things on fire and explode things and so on. It's gotten to such a point now that I saw an ad in the chemical engineering news about a chemistry set that didn't have chemicals. The lawyers have taken over. You can now buy chemistry sets with no chemicals. So I'll start first by talking about how you power particle and fluid motion, and towards the end I'll talk about this collective behavior where they communicate with each other. Now, why do we want to do all this? For a variety of reasons, as models for living systems. Living systems are beautiful, but they have one big problem. They tend to die. You have to treat them well, you have to feed them, blah, 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 blah. These things don't care. Okay? They do not need TLC. So, there are some more practical reasons. You might want to have motors on nano machines, biological cells. You can think of roving sensors. Right now, most sensors stay in one place, wait for the analyte to come to them. And you could think of these things as going around hunting for whatever analyte there might be. Active delivery vehicles, so nano dump trucks, if you will. So, for example, if you now have, let's say, an infection in some part of the body, you take an antibiotic, and it gets there through passive diffusion. And ideally, as I showed you in that nano submarine, you want to just load it up with drug and have it go straight to wherever you want it to do. And want it to go. And so that will allow you to directly deliver something, maybe make patterns, and all kinds of stuff. And also, and I'll talk about these two later on, by the reverse, Galilean reverse, you should be able to pump fluids. So rather than move the object, keep the object stationary and pump fluid. So I'll talk about how you can build pumps that have no real moving parts that can pump fluids. You don't need channels. You can direct the fluid flow and so on. And we want to do everything through catalysis. So I assume everyone knows what catalysis is. They do not know what catalysis is. Okay. The catalysts are things that just speed up reactions. It's just the simplest possible way of describing it. And so since we are going to take a leaf out of biology and use chemical reactions to engineer movement, just like in biology, we're going to use catalysis. So instead of enzymes, which are common in biology and they are used to do catalysis, we might use other kinds of catalysts, but the concept is essentially the same. just a point here, you're not trying to move ensembles of objects by applying an outside field. Okay? If you have charged particles, you apply electric field, you can move the whole thing. If you have magnetic particles, if you apply a magnetic field, you can move the whole thing. That's not what we're trying to do. We are trying to power individual objects so that they will move on their own, just like the biological examples that you saw earlier on. That's what we want to try and do. Have them each move on their own. And so for that, you need catalysis because you want to turn chemical energy into mechanical motion, but also you need asymmetry. Because if you generate gradients all around it, of course, there's no net force, you go nowhere. So those are the two things that you need. And we're talking about nano and micron size objects. They're too small to carry their own fuel tank, right? And so they have to use what's around them to generate the energy. Yes?
I'm not sure you really need catalysis to use this larger way. There are some surfactants that change the configuration when lighting is blue, and with some genus, with transfer usage, you really can make the surface.
Yes, except that they won't move forever. So a good example of that is, so the question is, do you really need catalysis? And a good example of this, what you just said, are the so-called camphor boats. So camphor is a solid, it's an organic compound, it's slightly soluble in water. If you just take camphor, grind them up, put it in water, they start to move. Why do they start to move? Because they slowly dissolve in water. When you ground them up, you make asymmetric particles. And the sharper edges dissolve because they have higher surface area, they dissolve faster. So around the surface, the sharper edges, the surface tension is lowered much more than in other parts, and that causes them to move. But of course, they won't move forever. When it all dissolves, that's the end of the story. Here, these motors, as long as you keep supplying them with food or fuel or whatever you want to call it, they will move. So that's why we need the catalysis. Any other questions? So we want to generate fields that cause them to move, and as I said, the energy needs to be harvested locally. It has to be around them. They can't carry their own fuel, they're just too small. Now, you might ask, well, okay, fine, ATP to ADP, but are chemical reactions in general, do they pack enough energy to cause things to move? And so this is just an illustration. So if we ask a chemist, what is the simplest reaction you can think of? More often than not, they'll just say hydrogenation of ethylene to ethane. Right? It's really a simple reaction. You can think of other ones, hydrogen and oxygen to water or what have you. I just took one example. And the amount of energy that's released in this is about 135 kilojoules per mole. So per molecule, so this is one catalytic turnover. So one turnover is a conversion of one molecule. And there are 6 times 10 to the 23 molecules in a mole. For one molecule, that's the energy that you get out. Now it suddenly dawned on me that I'm talking to physicists, so I converted that into KT last night. So let's say you want to move a particle 10 nanometers in diameter, about 100 nanometers in 1 second. You can easily calculate how much energy you need, force times distance. That's the force. And that's your distance. And in a viscous medium like water, the energy you need is 1 0.9 times 10 minus 24. That is 5 orders of magnitude smaller than that. So a single molecule of ethylene being hydrogenated releases 5 orders of more energy than you need for this. So you can have the most inefficient system. And Pico was talking about some of these nano micron size things having 1% efficiency. That's plenty. Now, that's not the only story, obviously. You have to keep kicking this thing. Okay, because if you give it one kick and it wait too long, Brownian motion is just going to randomize it. And you're not going to have a net movement in any particular direction. So you have to keep kicking at it. But the point here is there's enough energy in just about every chemical reaction you can think of. Which means you can take just about any chemical reaction and should be able to build motors based on that. Now, a lot of you know about Reynolds number. The only point I'm trying to make here is that if you're working the low Reynolds number regime, you have to worry about surface forces. So obviously miniaturizing a car is not going to work with. You have to generate forces, surface forces, because that's all you have. So you have to think about viscosity and surface tension and diffusion and electrostatic forces, and try to use these things to generate motion. The given wisdom is inertia is not important. I guess that's not quite true. As you saw, you can transfer momentum to tracer particles from biological engineering. So I guess there is some transfer of momentum that's possible. But in general, that's what you should be worrying about. Surface forces. How do you generate surface forces? Well, so the Scallop theorem that Pecco talked about, that if you have a purely time reversible reciprocal motion, then you do not see a net movement, although as I pointed out, and I'll talk about it towards the end, in real life that's not quite true, because in real life you have Brownian rotation, which rearranges these things, and you can have an actual motion from point A to point B, even though you're doing reciprocal motion. Okay, so talk about a few things. I want to talk about how you move things, how you can load them up, move the cargo, drop them off, etc. How can you direct the motion, so phototaxis, chemotaxis, so these are all synthetic systems. And then I'll end up by talking about how you can have them talk to each other. So that's the general plan of action here. Questions? Okay. So we'll talk about these 4 things, and also I will talk about different length scales. For the most part, what you've heard here, the smallest length scale has been maybe 1 micron or so. And I'm going to talk about what happens when you go all the way down to maybe 5 nanometers, 10 nanometers, individual molecules. So that's the other thing I want to talk about. Okay, so this is this was our original motor, and it's a very simple design. It's a rod that's about a couple of microns long. Half of it is platinum, half of it is gold. It's about 300-400 nanometers in diameter. I'll talk about how you make them in a minute. In this case, the fuel was hydrogen peroxide, and it moves. And we'll show you, we'll discuss that in detail. So how do you make these things? Very, very easy. You take aluminum membrane, so you can buy these in bulk. Okay, these are used for filtration, and because they are used for filtration, they have channels through them. So these are the channels. Unfortunately, they're not perfect, so they tend to splay out at the bottom. And so what you do is you first of all evaporate some silver to block this part where things are sprayed out, so you have no nice channels. And then you do electrochemical deposition. Very simple. You just do reduction. And depending on the metal that you choose, you deposit whatever metal you want, platinum, gold, nickel, what have you. And depending on how long you do it, each segment length can be varied at will. So in this case, you first deposit gold, and then you deposit platinum, for example, or you could have done it in the reverse way. And then typically you come in with an acid to dissolve away your silver. Gold and platinum are acid resistant. And then you come in with a base, and base dissolves the alumina. And so in one afternoon you can make millions of these things. Not hard at all. So these are how you make striped rods. You can have multi-metallic striped rods. I showed you the gold platinum one, but you can make many different striped rods. The other kind of asymmetrical particles that you can have are the Janus particles. So Janus is the two-headed Greek god. And so Janus particles have two faces. Sorry, two faces. Okay. I guess one head, two faces. Okay. And these can also be made very easily. What you do is you can buy particles, silica particles, polymer particles, and you drop them in a mixture of water and organic. And of course, they float on water in the form of monolayer here. You have a glass side, slice it to the bottom, and slowly pull it out. And so this layer then deposits itself in the slide, so you're just pulling it out. Turn it over, and have metals evaporate, for example. And of course, since you evaporate the metals in the bottom, this side remains uncoated, this side gets coated. And that's how you make it. Okay? These are some examples. These are polystyrene polymers. So that's what you start with, and you, through the procedure I just told you, you can deposit gold on one side, and you can see this. Works very well. Works very well. So the nice thing about this is A, they're asymmetric because the two faces are different. B, you can functionalize them on both faces. And so you can deliver things from both faces. You can make one face hydrophobic, the other face hydrophilic. You can make one face positive, another face negative, whatever you want.
Okay. I guess they're much lighter than the bimetallic ones too, so they're quite a
Yes, right. Yeah, absolutely. Well, it depends. I mean, I could have started with one metallic sphere and then deposit another metal. Sure, absolutely. So then what we do is we just put them on, we suspend them in water, for example, drop them on a microscope slide, put on a cover slip, and watch them move. Okay? Not a high-tech thing. Now, in theory, they're smaller than the wavelength of light, but it's scatter-like enough that you can see them. So that's not an issue. Now, to get back to your point about density. So if you have these metallic rods, they sink down, but they don't actually touch the bottom glass slide, and the reason for it is the double layer. Most metals tend to have a negative zeta potential, negative charge on the surface. Glass slide is also negatively charged, so they're sort of like this. They don't actually touch the glass slide. So, I'm going to show you a couple of videos, but I'm going to talk about mechanisms of motion and so on. But I sort of thought of at least tell you before I show the videos how this particular rod moves. So remember I said that the fuel in this case is hydrogen peroxide, and the overall chemical reaction. So, okay, nothing to get scared about. This is only one of 3 reactions over 3 days. Okay. The overall chemical reaction is hydrogen peroxide into water and oxygen. Okay? That's the overall chemical reaction. Now that is what we call a disproportionation reaction, i.e. what that means is half of the hydrogen peroxide is getting oxidized and the other half is getting reduced. And the reason we have 2 different metals is that platinum catalyzes the oxidation and the gold side catalyzes the reduction. And so in the platinum side, what is happening is hydrogen peroxide is getting oxidized, you make oxygen, and you make 2 protons and 2 electrons. On the gold side, hydrogen peroxide gets reduced, and you make water, and you consume 2 protons and 2 electrons. So if you add the whole thing up, of course, the protons and electrons cancel. All you have done is taken 2 hydrogen peroxide molecules and made oxygen and water from it. Okay? The overall reaction is that. But in detail, what you're doing is you're making protons and electrons and platinum, and you're consuming protons and electrons and the gold atom. And the electrons, so this is like a short circuit fuel cell, if you will. The electrons flow through the metal from the platinum side to the gold side. The protons have to follow the electrons. The protons, of course, hydrated, so they drag fluid this way. From the platinum side to the gold side, the fluid is dragged. And so relative to the fluid, the rod moves platinum end forward. Remember, it moves platinum end forward. I'll show that to you, but just remember that. If you prevent this from moving, it will actually pump water. Okay? And I'll show you that also. There are no moving parts, but it'll pump water. So let me show you a couple of videos. So you see these rods, and the next, yes.
Does this process degrade the platinum or the gold, or can it
No,
happen
so
indefinitely?
no, it doesn't. So that's why we call them catalysts. So the definition of catalysts is that they don't degrade. Now, having said that, that's an overstatement. Most catalysts eventually croak. But these things will go on for a very long time before they start to get poisoned. So the video you'll see on your left, you'll see these rods in just pure water. They're doing Brownian motion, jiggling around. And on the right, very dilute, 2.5% hydrogen peroxide. So this is Brownian motion, and you can see these little buggers. They look like bacteria. They're about the same size as bacteria, 1 to 2 microns. You know, some of them come together when they start to rotate. Here's one. By the way, I think every video that I will show you is a real-time video, not speeded up, not slowed down. So this is exactly what you see. So, they look like bacteria. The first question is, okay, so how fast are they moving? So here's my scale. So, yes.
Sorry, I just want to make sure I understand what's going on here. So, 2 slides
Oops, sorry.
previously.
Back up. Yeah.
So here, if this is just put into water,
Yeah.
wouldn't the gold side, or wouldn't the platinum side? Oh, actually, never mind. They have it.
Yeah. Try not to file a patent for perpetual motion machine. The patent office tends to look down upon it. Okay. Yeah, so this is the scale. The cheetah is still our champion. I don't even come close to that. Okay? Some of you might, but I don't. They're about the same speed as flagellar bacteria. Brownian motion, which of course has no real directionality, is much slower. And you might say, why do I show them as body lengths per second? This is just to illustrate that absolute speed is limited by body size. When you give these talks to non-scientists, you have to be very careful. Because the Michael Crichton's book, Great, if you have read the book, it talks about these nanobots, the gray goo, running down human beings and doing bad things to them. My point here is absolute speed is limited by body size. You can try to run as fast as you want. They're not going to catch you. You're okay. So that it's important to point that out. I also gave a talk in Germany one time. This was a strange conference. There were a few scientists like us, and then there were theologians and philosophers and so on. And I call these things autonomous objects because they move on their own. And so the philosopher comes up to me and says, "You call them autonomous. Do they have free will?" So it's important to make sure that people understand what you're talking about. Yes.
So, did you notice any anomalies in the diffusive behavior of these particles? Because there should be some finite concentration of H2O2 and H.
There should be what?
Isn't there a finite concentration even at
So the way we run these reactions, even at 2.5% H2O2, the amount of fuel is so much more than these guys that they will go on forever. So what you're saying is what happens when you start to run out of fuel, right?
Or just in regular water, is there any difference? Or from what a rod-like particle would do without any electrode?
Well, if you don't give it fuel, then of course, as I said, I guess we didn't, sorry, I'm going backwards. Whoa. This is not a great movie. But I guess if you had a high enough density of them, then you would start to see some interesting effects in the way you talk about it. But we haven't done those things. Yes?
I'm still a little confused about the mechanism of propulsion.
Yeah.
So you're also, I guess I'm wondering if this is the dominant effect, the electrokinetic propulsion, because you're also creating a gradient of oxygen.
It's a very good point, and I'll come back to that later, so hold on. So they're moving at a decent rate. So the next question is directionality. And so the way we sort of define directionality is if the rod is pointing this when it keeps moving, that's great. And we can define an angle of theta. It moves orthogonally, then theta is 90 degrees, and you can talk about the cosine of that angle. You can see that on the canvas. Cosine of the angle, and so it's moving it starts to move orthogonally. Cosine theta is 0. If it's keeps moving the same direction, cosine theta is 1. So the directionality should be as close to 1 as possible for it to be useful. And the forward velocity is then simply a center-to-center displacement times the directionality. Now you have to define over what time interval, because at the end of the day, at long enough time interval, they're all random. So these are, I guess that's the end about maybe a second or so. So the directionality, the faster rods have reasonable directionality under this definition. Now I'll talk about how you can improve the directionality. But the slower rods, presumably they're not as catalytically active, they're not turning over hydrogen peroxide fast enough, so they're not moving as fast, and the Brownian motion is creating problems for them. So they start to lose the directionality. Here's some raw data. So here's the speed, here's the directionality, here's the forward velocity, if you will. So in pure water, there is some movement. This is, of course, Brownian movement. The directionality is essentially 0. So the forward velocity is close to 0. And then if you add hydrogen peroxide, it keeps increasing. The directionality increases and forward velocity increases. But note that starts to level up. And so you might ask the question, why does it level off? Why doesn't the speed keep going up and up and up? And there are two possible reasons for this. Now, the speed is related to how fast you're consuming your fuel, hydrogen peroxide. And the two things that govern that, one is diffusion. If the hydrogen peroxide does not diffuse fast enough to your catalyst, then you're going to have, that would be a limiting factor. The other is catalytic turnover, which is that it can diffuse as fast as it wants, but if the catalyst is slow, then that's your limiting factor. And so those are the two things. We can calculate what the diffusion is going to be, and we can calculate the turnover by just measuring oxygen evolution. And it turns out it depends on the catalyst. And so higher the surface area of the catalyst, the faster the rods should move. And Joe Wong at UCSD has made these rods where he incorporated carbon nanotubes into the platinum end. Basically, just increase the surface of the area of the platinum by putting this stuff. And they move much, much faster, as you can see. In fact, I think his latest ones would move like 100 microns a second. So you can easily speed up the reaction. So it's not really, he calls it better gas mileage, it's not. Because you're still consuming more hydrogen peroxide, which is doing it faster. But anyway, so there are ways to speed up these things if you wanted to speed them up. The other way you can do it is, of course, all chemical reactions have an activation energy, and the purpose of the catalyst is to lower the activation energy so the reaction is faster. And the other way to make a reaction faster is to just raise the temperature. So the same rods at higher temperatures should go faster. So Joe Wong proved that. Also, he could turn on and off the speed of the rods by varying the temperature. So I guess I don't have the temperatures here. But anyway, you can see at a certain temperature, that's the track for a given time interval. And at a higher temperature, you get a much longer track with the same time interval. So you can speed these things up by putting in a better catalyst, or you can speed these things up by raising the temperature. So there are several knobs that you can turn to move them faster.
So in that case, you'd also be increasing the thermal fluctuations.
Yes.
So you probably,
Right.
you
So-
could
so-
still get an improvement in the direction.
Well, you can see it here, so I guess it's speeding up faster than you're increasing the thermal fluctuations. Right, and it's obviously a trade-off. Now, back to this question. The mechanism that I showed, is this the only possible mechanism? What about oxygen bubble that you get? In other words, the question is, are these like rockets that you're making gas at one end and it's causing it to move like this? And I'll show you some rockets that do move like that. But remember, you have a platinum end and a gold end, and the oxygen is being made at the platinum end. So if these move by rocket propulsion, they should move gold end forward. The platinum would be at the back side. But they move platinum end forward. Actually, we thought they were going to do exactly the way you suggested, bubble propulsion. It turns out they don't. How do I know it? Here's a rod. It's pretty clear which side is platinum, which side is gold. You can see it. And when it's in motion, you can see it's moving from right to left. It's moving platinum end forward. So it does suggest then that it is not a bubble propulsion. You can make motors move by bubble propulsion, as I said. I'll show you some examples. This is not. Yeah.
And what about diffusion-phoresis then? The gradient of oxygen causes chemical diffusion-phoresis on the colors, right?
Yes. We've done some calculations. By we, I mean my physicist friends. We've done some calculations. In fact, that's too slow. There's one other mechanism, which is interfacial tension mechanism, because water with oxygen dissolved in it has slightly lower surface tension than the other side. And when we first send this paper in, that's what we proposed. And it turns out we were wrong. So we're left with, having eliminated all the mechanisms, we are left with this mechanism that I talked about. Yes?
Sorry, you mentioned interfacial tension.
Yeah.
Are these in a bulk solution or are they at a fluid interface?
They're in water with hydrogen peroxide dissolved. But oxygen is non-polar. And so when you dissolve oxygen in water, the polarity goes down a little bit, just a little bit. Yes?
Can you get them to sit in the surface, and do they do anything different?
Here's one example, and I'll show you one.
So can I ask one?
Yes?
So you mentioned momentum recoil.
Keep asking questions. I've got 4.5 hours. Yes?
But I was wondering, so we are still at very low Reynolds numbers, right?
Yes.
So in any case, it can't be like a momentum recoil. Is that wrong? I mean, it's
You're
not.
asking me, you should ask these guys.
I mean, I thought
But then you have to explain to me, after Pecco made it very clear that there is no concept of inertia and momentum in low Reynolds number. And you saw Jerry's experiments where the tracers get affected by these little guys moving around. My colleague Tom Maluk published with a group in ESPACI in PRL recently, where again, if you compare these rods with bacteria and tracer particles, and these rods basically perturb the tracer particles just like the bacteria do. So there is some transfer. Now, why, how? I have no clue.
What's the question?
What was the
The
question?
question was that if there's no low Reynolds number, no momentum transfer, you're making bubbles, you should not be moving things by recoil. That,
Yeah, because you said we're eliminating mechanisms, and I was thinking, well, this wouldn't be the mechanism anyway because you're at very low Reynolds numbers, so you have what you have there.
yeah.
Thinking about the directionality,
Yes.
have you considered different geometries for the point where they're joined, try and make them more sort of stable in a straight line?
It's a very good question. See, this is the problem with theoreticians. They can conjure up all the different shapes and sizes and so on and do calculations of them. Try making them. It's easy to make rods and it's easy to make rounded spheres. Okay? Now, there's one that we're thinking of, and you have to tell me whether the physics is against this, which is, you know, when you fly a kite, right, the tail is important. Why is the tail important? To me, it maintains the memory of where it was oriented. And so if you put a tail on it, it should move straighter. A flexible tail. Is that crap? I don't know. We're trying to make them. And I think we can make them. We haven't tested them yet. Any other question? Yes.
They're really heavy, so there must be sedimented close to the interface, right? The glass cover slide, or
So
does the interface have an influence of their swing speed?
not as far as we can tell. You can make them lighter by putting polymer segments in them.
So they swim on any kind of surface.
And I promised you that I'll show you one that floats in water. So I'll show you one of those. Okay, so the velocity should scale as the electric field. If this is the mechanism where you have oxidation on one end, reduction at the other, electrons flowing through the rod, protons and water flowing from one side. So the velocities will scale with the charge on the rod. And by the way, that suggests that if you reverse the charge, the rod will move in the opposite direction, which is kind of interesting. But also the electric field. The electric field is, of course, the current density over the conductivity of the solution. So if you knew what the current density was, we could say a lot of nice things about these. So how do you measure the current across this 2-micron thing running around in water? Well, ideally you want to put an insulator, put a nice meter. You measure the current. I don't know how to do it. So we cheated. What we did is we just took interdigitated platinum gold microelectrodes, put it in hydrogen peroxide, measured the current. Okay? So that's what we did. So basically what we're saying is you put a gold and platinum into hydrogen peroxide, hook them up, you should see a current. And you do. So this is baseline water. This is 0.5% hydrogen peroxide, 3% hydrogen peroxide. So you do see a current. You can sort of calculate the electric field, about 13 volts per centimeter. Okay? So these are not small electric fields being generated by these redox reactions. It's substantial. And this will, of course, vary with which metals you choose, et cetera, et cetera. And so if you knew the direction of current, platinum to gold or gold to platinum or what have you, and the magnitude of the current, you can say things about these rods. And we went through the periodic table and measured currents and speeds and so on, and basically the prediction works out fine. So you can basically take most metal pairs, and as long as the different activities don't work. The other thing is, remember that the speed should vary with current density. So if we could screw around with the current density, we should be able to modulate the speed. And so what we found is if you put alcohol into water, you start to poison the gases. And when the current density goes down, the velocity goes down, then you get a straight line. So basically, these rods slow down when you add alcohol, much like us. Okay? I'm trying to draw an analogy to biology, okay? You can plot it in a different way. The ratio of speed divided by the zeta potential over the current, and it's the same relationship. Essentially, and you get a straight line. So it looks like this mechanism that I suggested, the electrokinetic mechanism, is a reasonable one for these systems. The other thing is that it's inversely proportional to solution conductivity. So, it went too fast. So in pure water with hydrogen peroxide, they move much faster. When you add salt, they really slow down, and you can see the speed increases with 1 over conductivity. Which is great for the mechanism, but it absolutely sucks if you want them to run around in your body. Because, of course, there's high concentration of salt in your body. So we need something else. These waters are useless. And so you notice how deftly I avoid physics. But if you're really interested, Posner has a 26-page article in Journal of Fluid Mechanics, which tells you in gory details all the physics of these rods, which everyone knows. And basically, it's the mechanism is exactly what we just suggested. In fact, this is from Posner's article. Now, so this general concept that you're going to have a redox reaction where you have oxidation at one end and reduction at the other end. And then you have electron go through and protons outside. By the way, this is a proton gradient driven motor. And if you think about biology, the whole biology runs on proton gradients. This is Mitchell's contribution. So it's kind of amusing that it's similar, but it suggests that any two redox pairs should work fine as long as you have oxidation at one end, reduction at the other end, a conductive pathway for the electrons to go through, and protons running around on the outside. It should work fine. So here is one that floats on water. It's an air-breathing motor. So what this one is first of all a carbon. It's so simple, it's almost stupid. It's a carbon fiber. It's actually pretty long, several millimeters long. And one side has been dipped into glucose oxidase enzyme, and the other side has been dipped into this reductase. And what happens is, in the presence of oxygen, glucose oxidase oxidizes glucose, makes protons and electrons. The electrons flow through the carbon fiber. Protons outside goes to the reductase where oxygen is reduced, and this whole thing moves. As I said, it's air breathing because it needs oxygen. So it floats on the water. If you prevent any oxygen from coming into contact with these things, they'll stop. So this is another design. It seems to be like a general principle for motor design, if you will.
So how large did you say it was?
This is long. This is several millimeters long.
How fast is it?
I don't remember. I'm sorry. I seem reasonably well. Yeah, I don't know these ones. And Peter Mitchell, who got the Nobel Prize for this proton motive forces biology running on proton gradients, he suggested back in the 60s that some bacteria might actually move by the same mechanism. So there are, of course, the flagellar bacteria that moves the flagella move. There are some polymerization bacteria like Listeria that moves by actin polymerization, much like what you heard this morning. And then there are others whose names I can't even pronounce. And they have no obvious way of moving, but they do move. And Peter Mitchell proposed that they move by this mechanism that I just talked about. One end of the bacteria is doing oxidation, the other end is doing reduction, and that's what's causing them to move. After he proposed this, Howard Berg at Harvard said that was total nonsense, and his argument is a good one, is that they move in salty water, and remember the speed is inversely proportional to the conductivity of the medium, so this mechanism cannot operate. I don't know, I'm just telling you what some of the suggestions in the literature are. Okay, so how can you make them more directional? Well, you could put magnetic strips in them. So here is one, platinum, nickel, gold, and again you make them using this aluminum membranes, and you just sequentially electrode deposit these metals and then free them off the membranes, and then you magnetize these little nickel segments, and now you should be able to control them using a magnetic field. So the engine is still hydrogen peroxide decomposition, but the magnetic field helps them orient. This is not a great movie, but anyway, when the field is off, they move in different directions. When the field comes on, they start to move liquids. And by the way, they're about the same size and magnetic moment as the magnetotactic bacteria. How many of you know about magnetotactic bacteria? So these guys have little magnets in them, and they're bottom feeders. And so in the northern hemisphere, bottom is south. And so that's how they use a magnet so they can go down to the bottom of whatever pool of water it is. And in the southern hemisphere, they do the opposite. Anyway. So the interesting thing is here, where we're looking at the rotational diffusion coefficient of these rods, these magnetized rods. So if you don't apply a magnetic field, nor do you give it a fuel, then this is the rotational diffusion coefficient, whatever it is, 200. If you now give it fuel but not a magnetic field, you give it power but no sense of direction, so they are like teenagers, right? And so they just go crazy and it goes up an order of magnitude. But if you then apply the field, you dampen the whole thing down, and then they start to move more directional. So you can do fun things. You can write this guy to the PSU. This is the P. When we first submitted to the good journal, one of the editors really hated this. And I said, look, just because my grad student has bad handwriting is no reason to reject the paper. So it did get published, but yeah, you can have. You can do more complicated things like a gear. So this is a bigger object. It's about 100 microns, and it's, these are not hard to make. You make them by lithography. So these are gold, and on each tooth, on one side and one side only, you have platinum. So if you put in hydrogen peroxide, it should rotate with platinum end forward, and its linear velocity should scale accordingly. The one I'll show you is actually upside down and it doesn't have PSU, but now, if you're wondering what are these things, these are posts. You try and nail this sucker down so it'll stay in place and rotate. You float it out. But it at least suggests that you can make little machines driven by catalysis, where so there's a little gear assembly, and you're going to power this gear by putting in platinum segments, and then you put in a little bit of hydrogen peroxide, it should rotate, and the other ones should rotate. So we'll see. That's not really what we're focused on, but if you really wanted to make a machine, questions so far?
Do you have a video of this one?
No, we haven't done it. This, I can't get any student of mine to do it. That's the problem. It requires going to the nanofab facility and spending hours there. If you want to join our group and do it.
Sorry, I'm committed to another group.
You've spoken for, all right,
Can I
fine.
just ask,
Yes,
does it need a post to turn?
does it need
So
a,
would it need a post?
well, otherwise you end up, well, it depends on the density, right? If the whole thing starts floating around, that's not so good, right?
No, but it rotates, right?
Yeah.
And can you show it again, does it actually rotate?
Which one? Oh, sorry. Yeah, it rotates actually. It's rotating. It's doing both. I mean, it's doing the processing and the rotation. Cargo. So this is what you'd like to do, right? You want to have a state cargo station where you pick up your cargo, move it to a drop-off station, then come back and keep doing this. It's a hard one, actually. But I'll show you what's been done. So first of all, it's easy to load up. That's not the problem. You can do it electrostatically. So what you do is you to the platinum gold segment, you add a polypyrrole segment, so you're doing electrodeposition, so you just polymerize a little bit of polypyrrole on top, and polypyrrole has a much more negative zeta potential than either gold or platinum, so that's really the negative end, and so if you have a positively charged particle, hopefully it lines up like this and sticks. I said hopefully half the time it's a little askew, and then it starts rotating as you move forward. Or you can do a covalent linkage using biology, streptavidin-avidin linkages, and both of them work fine. So here is this four-limbed rod carrying this big cargo on its back. You can barely see the cargo, but see it. Carrying it. They move more slowly because of the increased drag force. Now, if they're not symmetrical, of course, they start to rotate. And after a while, it says, heck with it, and throws it out. Look at this one. That's not quite what you want. So they move more slowly because of increased drag force, because you have the big ball it's carrying as a bag, and you can model this thing, and it works pretty well. So these are some of the model predicted, and this is what we see experimentally, and it fits reasonably well. So we can, and of course you can, move them to a specific location by putting in magnetic strips and using a magnetic field, etc. The hard part is having them drop off. So Joe Wong's group has, what they do is they have a drop-off station of magnets that move it. And the cargo is attached magnetically, so it falls off. It's by mechanical vibration, but that's just not an elegant way of doing it. We have a way that we published where we have a photocleavable linker, so you have the light shine exactly where you want it to be dropped off. And the light cleaves off the linker, the cargo drops off. That's bad too, because you can only do it once. And then you can't come back and pick up again. So we need to think of other ways of doing this.
So I guess all these, the rod is pulling the cargo. Is that
In this case, let me see what the configuration was. Oops. Keep going in the wrong direction. So the cargo was at the back. The platinum end is the leading end. So you can see that the cargo is at the back. In this case.
And the reason I ask is that the hydrodynamic flow fields, that something that's a puller versus a push object produced are different. And so if you have a whole bunch of them, they
Should we be pushing or pulling?
Well, if you want to have things that,
I mean, you can do it both ways in principle.
the collective behavior should be, it depends on what you want. If you want them to all swim in the same direction, both have their difficulties.
Yes, sir.
Would an optical tweezers work
This
to
time
rip,
he's working for Yes.
would an optical tweezer work to rip the cargo off?
Say that again?
Would an optical tweezer work to rip the cargo off?
We haven't tried it, but that's certainly a possibility, yes.
Don't the metal bits tend to be repelled from the optical track?
That'd be the idea, yeah.
I guess that would be the
Yeah.
Can't spin them or shield them. Optical tweezers are very hard to use them.
Every time you try to trap these with optical tweezers, a giant bubble of oxygen appears. It's kind
No,
of,
we have other ways of moving things which I haven't talked about. This is just one example. Powering motion, but I'll talk about other ones. Yes?
Because we talk about transport and dropping off the cargo, you actually have to think about shielding the cargo before it comes to the drop-off station, because it might dissolve earlier while it's transported.
So the photocleavable linker where we link the cargo, I guess I should have put a slide in. With the motor, what you can have is a mask, and you shine light from the top, right? And the thing is moving. As soon as it comes where the light is, it drops it off, and it moves on. The only thing is I can't then go reattach another cargo. Is the problem. There's another question back there. Okay. So it's talking about motors, right? Well, the Galilean inverse is the pump. So the motors are moving. Of course, if you are an observer sitting on the motor is not moving, the fluid is moving in the opposite direction. And therefore, if you prevent this guy from moving, it should pump the fluid. So the setup there is that I have one metal, and then I put the second metal here. And we want to see how the fluid moves. And now, of course, it's a closed system, so you're going to have convective rolls. And to see the fluid, we throw in tracers. So here is gold, and for whatever reason, I think you're trying to save me some money. It's silver, actually, not that. And it works the opposite way, but that's a different issue. And you can clearly see the tracers moving back and forth. In fact, if you focus down, you will see that one set is out of focus and the other set is more in focus. So they're coming in, they're moving out, and one is in focus and the other one is not. They come at different levels. And you can make patterns and so on. So everything looked fine until we started screwing around with the tracers. It depends on what tracers you have. So if you had little gold rods as tracers, they come in. So this is silver feature. This whole thing is gold. So this is the thing. They come in and they come in very close and they start to do convective rolls like this. If you have, so these are slightly negatively charged. If you have negatively charged polystyrene, they come in from long distance again, but there's a zone of exclusion which they dare not enter. Okay? Same with negatively charged silica particles. They will come in long distances, make a nice close packed structure, but there's a zone of exclusion. If you have, so these are for negatively charged particles. If you have positively charged tracers, they come all the way in. So these are amidine particles coming all the way in. Look closely, they come in and then lose focus. The reason is they're coming in and they're going up. It's the convective rolls. So the negatively charged ones will come in, but then there's a zone of exclusion. The positively charged ones will come in all the way and move on. So these will come in all the way, positively charged ones, here. Come on. And negatively charged ones have this zone of exclusion. Now, if you have an insulator that separates the two metals, silver and gold, then of course everything should come to a stop, because this mechanism will no longer work. This mechanism depends on electron flow from where oxidation is taking place to where reduction is taking place. And indeed, if you put a little bit of glass there, all you see is Brownian motions of tracers. There is no net movement. So this is a very brief summary of what's going on here. So here's your gold, here's your silver, and it turns out, remember in the platinum gold case, the platinum was where the oxidation was taking place, gold is where the reduction was taking place, and the silver gold pair is the opposite. You can see that when you measure the direction of current and so on and so forth. And so in this case, gold is where oxidation takes place, silver is where reduction takes place. And so electrons go from gold to silver, protons go along the surface to silver, drags water. Remember, the metals have negative zeta potential. So in the double layer, you have the positively charged protons. And so the protons and the associated water being dragged in. This is electroosmosis. So there's a net flow towards the silver. And that's why particles will come from long distances towards the silver. But if you're a negative particle, as you come closer and closer, since this is the negative end of this metal pair, they get repelled. So when they come very close, they start to get repelled. So you have a zone of exclusion. If it's a positively charged particle, that's great. It just keeps going and then it goes up. So that's the story. It's a combination of electrophoresis of these particles and the electroosmosis of this fluid flow along the surface. Oh yeah, anyway, again, just to show, you can measure the speeds of these tracer particles, and you can also measure the speeds. These tracer particles, of course, also move in an applied electric field that's externally imposed. And you can see what the equivalent speed is, from which you can calculate what the electric field we're generating through these redox reactors. And again, I showed you 13 volts per centimeter. These are substantial fields. So these white ones are by this catalysis. This is by an applied electric field. So we're talking about 10 volts here, same here, 10, 20 volts per centimeter. So you generate fairly large electric field through these reactions, these redox reactions that are going on. I got a few more minutes, so some. That's okay. These are the gold tracers which go back and forth, back and forth. So the convective rolls. Whereas the positive charged ones come very close and then keep moving. Anyway, someone was interested in bubble-powered motor. So I have a bubble-powered motor. So, there are many ways you can move things. So, this is not our work. This is work by Sanchez and in Dresden and by Joe Wan at UCSD. And I won't go into gory details of how you construct these things, but you can have rolled up tubes. Okay? And in this case, the inside of the tube is platinum. And it's only one metal here, so there's no redox reaction going on. Just one metal. And so what happens is the hydrogen peroxide goes in, platinum decomposes it to oxygen, bubbles are formed, shoot out, and this one is a rocket action. So, and there are many different kinds of motions. So this is a sort of a linear motion, and there's a circular motion.
So what's the scale here?
So these are moving much, much faster. So this is depends on how you construct these tubes.
Wow. So it breaks symmetry, I guess. You could go either.
So the way you construct it, that's an important question, because in principle they shouldn't move, because if you have oxygen bubbles coming out of both ends. It turns out that the way you make it, you don't have to do anything special. One side is tapered. And so this is the mechanism that suggests where the hydrogen peroxide enters, oxygen is being formed, and the bubbles are expelled from the other side, the wider side. And just like ours, there's a saturation, which is catalysis limited, so just upping the hydrogen peroxide concentration doesn't necessarily speed up these things. You reach a limited thing. So, yeah, so these are what? This is about 250 microns per second. So, in case you guys are interested in rockets, our stupid motors, which are going like 10, 20 microns per second, is a lot slower. In terms of body lengths per second, they're faster than the escape velocity for the rockets that are used now. to put things in outer space, and these are much, much faster. You can also do this magnetic trick, right? So inside layer is platinum, and then one of the other layers is a ferromagnetic thing, and then you can have a, you can control this. These things, if you're wondering what these are oxygen bubbles.
That's synchronized swimming.
What?
Synchronized swimming.
Yeah, there you go. Yeah, if we run out of funds, we're going to have these things, right? Like slot machines, and you bet on these things. And then you can have them carry cargo. So here's a cargo, here's one of these guys.
So the bubbles dissolve back in pretty quickly.
You don't see the bubbles?
So we don't see the bubbles, we don't see any bubbles in fact, because the bubbles are not formed where platinum is. You just get a supersaturated solution. Every so often, someplace in solution, you get a nucleation and the bubble is formed. So you can have real fun with these things. They got into the Guinness Book of World Records, by the way. This is their certificate. But you can do some really interesting, serious things with these. Here is, sorry, I'm wrong. Here is one where you can functionalize these tubes so that they bind to specific things and maybe carry them. So if you have a bunch of different kinds of cells with different receptors, you can functionalize these tubes so that they can pick up only one kind of cell and move them. And so here is one that was published in Nanorod where they specifically picked up cancer cells. And so you have a pool of these cells, and these rockets come rushing in, picks up these cancer cells, go through the second chamber where you could analyze them. So you're physically isolating and separating. Okay, I think I'll stop here. Questions? Arnie or beverage?
I
Yes?
don't know, you might have mentioned it, but have you tried using ultrasound to actually get rid of the cargo? For example, if you make like micelles, like bubbles, holding the cargo. There's a lot of research done on like bursting these cargo-filled bubbles.
That's actually an interesting idea. The short answer is we have not tried.
This is also very local, like in the body where you can apply ultrasound.
We should try it out. Send me your name.
Catherine.
If it works, no. If it works, we'll have to put you on the list of offers.
Oh. Yeah, I don't know, just saying that.
Yes, sir.
So what about all that peroxide in your body? It's so little that it doesn't matter?
Look, the only, I'll get back to this later on with you. If you want to move these things in your body, the best fuel is glucose, because your blood has a lot of glucose. And I showed you a glucose-powered motor, the carbon fiber that had glucose. And so you want to use enzymes that use substrates in the body. The reason you want to use enzymes is basically you want to fast catalysts. So that's one of the things we are trying to do, and I'll talk a little bit more about it, but yes, that's what, no, hydrogen peroxide is bad. Yes.
I don't know if this will do anything interesting, but for the electrode fluid flow, where you have the different tracer particles, did you use Janus particles at all?
In these cases we didn't, but you're right. They should move with one face, oriented. By the way, I didn't talk about it, but these rods, remember the equation that the velocity is proportional to the zeta potential? So if you flip the zeta potential from positive to negative or vice versa, they'll flip the direction of motion and they do. So there's another piece of engineering you can do, but yeah, sure.
We can think of plenty of oxidation reaction, right? And why is the only reaction that works is with hydrogen peroxide? Why not with RO or other stuff?
Well, I showed you two. I showed you the hydrogen peroxide. I showed you the glucose oxidase. We published paper on using hydrazine as redox. So the only restriction there, and we haven't published, but we can use bromine. The only restriction there is you do not want to use something ionic. And the reason has nothing to do with the motion per se, but if you have a high enough ionic concentration, A, you slow down the motion because of the relationship I showed you, and B, they start to stick because you compress the double layers. And so while they're floating on the glass slide like this, now they start to stick. So those are the only two things. By the way, there was a paper which did this calculation about if you had glucose-powered motors in your body delivering drugs. Remember, it requires oxygen. And the question was, would your body be deprived of too much oxygen? Because the motor is eating up the oxygen in your blood. And the conclusion was yes. Any other questions?
So you need to like the oxygen tank next to you.